My guest today is Professor Wendy Freedman, who's Professor of Astronomy and Astrophysics at the University of Chicago. Her current projects involve measurements of the Hubble constant, the current expansion rate, as well as the past expansion rate, providing constraints on the acceleration of the universe and dark energy. Welcome, Wendy.
Thank you very much. Nice to join you.
Yeah, thanks for doing this. So you are one of the very few guests on the program that appeared more than once. And I remember our conversation like 4 years ago now. And we're going to talk a little bit about JWST. So I remember I'm saying something like, when JWST gets there, or I said something like, if JWST get to L2, you'll get beautiful data. And you corrected me. You said, when JWST gets there. And it's pretty cool. It got there. I think our engineers, give them a problem, they will make it happen. Voyager 1 is, I understand, still calling back after 50 years. And so engineering, we got that done.
Well, the engineering, I think, is a tremendous feat. And despite the fact that I said when, I think there were over 350 things that could have gone wrong. And if any one of those had gone wrong, we would not have had a JWST. So it really was a tremendous feat, an engineering feat. And I just feel very honored, lucky to be able to use this facility. It has really revolutionized so much of what we do.
Yeah, and the NASA engineers have done this over and over again. And so politicians wondering about funding, I mean, this is just a little bit of a tangent here. This is what makes us better, right? And we spent a trickle of the 35 trillion economy that we are sort of managing, a trickle.
Yeah, I think it is a tremendous example of so many things. I mean, there were, several thousand people who were involved overall in the putting together of this facility worldwide. And when we put our minds to it, we collectively, humanity, can do really, really important and exciting things. And I think JWST is an example of that. This is a facility that's operating 1 million miles from the Earth. It could not be serviced the way Hubble could be serviced, just nearby. And in it, these giant mirrors unfolded in space, and these giant sun shields that had to unfurl, and pins that had to come in and lock them into place, and they're the comparable to the width of human hair, and all of this fantastic technology worked. So we can do incredible things, and yeah, I think we just need to take a moment and take that in. It's amazing. And it's scary to think that these kinds of things could be cut, because they're opening up new windows on the universe. We learn new ways of using technology, and I think it benefits everyone, including just our appreciation for the cosmos that we live in.
Yeah, so my pessimism was more from, sort of the binary outcome of an engineering feat. And as you say, there is 35,000 things that could have gone wrong. And you're going to multiply all those probabilities. At the end of that probability is very, very small probability that things are going to work out. And everything seems like everything worked out.
Well, it sure did. And yeah, there were 350 catastrophic like failures that would have caused the mission just not to work at all. But probably, as you say, 35,000 little things that would have contributed to worse outcomes, and everything worked flawlessly. And as you know, it wasn't without a lot of challenges. This was an extremely challenging thing, and it was hard to do. There were mistakes early on that got corrected, and then we get this magnificent facility.
Yeah, so I'm getting a bit of an echo, Wendy, so I'm going to turn off one thing here.
Okay.
Should be better now. I hope. So I want to go into the status report on the Chicago Carnegie Hubble program, CCHP, measurement of the Hubble constant using the Hubble and James Webb Space Telescope. So you say here in abstract, we present the latest results from CCHP to measure the Hubble constant. Still getting a bit of an echo. Could you just turn down your volume a little bit?
Does that help?
Yeah. So using data from the JWST, and the overall program aims to calibrate three independent methods. Tip of the red giant branch, we talked about it last time. JAGB, which is sort of new, J region asymptotic giant branch stars, and Cepheus, which have been there forever. And so three independent methods. So you're looking at a galaxy, and we're using three independent methods to look at a singular target and try to see if the measurements that you're making sort of align, right?
Yes, so that was the goal of the project. And as you say, Cepheids have been used now, well, for a century, since Edwin Hubble used them to measure the distances near my galaxies, and then ultimately to show that the universe was expanding. So they have been our gold standard. But my feeling is that any method that we use in cosmology will have its own set of systematic uncertainties. And we can't determine either the sense or the size of these uncertainties using that one method alone. And in order to constrain these types of systematics, we need to make measurements in different ways, and each of the different methods will have its own set of systematics. But it's by combining those methods ultimately that we can get an overall constraint on the systematic uncertainties. So our proposal to James Webb was to use these three different indicators, the Cepheids, the tip of the red giant branch, and a new method, the carbon stars, what we've referred to as JAGB stars. It's a new method that Barry Medor and I developed a few years ago, informs the thesis now of a really talented student, Abby Lee, and to measure the distances to the same galaxies and determine whether or not the distances showed a large dispersion, whether they all agreed, whether a couple would agree and there would be an outlier. But the overall goal was to test them and see how well they would agree. And ultimately to tie into type 1a supernovae that we can observe much farther away and determine the Hubble constant.
Yeah, so just to set the context, Wendy. So we have sort of a general audience. So we're talking about the Hubble constant, typically referred to as H naught, and H naught is sort of the expansion rate of the universe here and now, at time equal to zero, so to speak. Mm-hmm. And what we're trying to figure out is, if we can determine this to some level of accuracy. And there are multiple methods by which we could potentially measure it. And one of them is to take a photograph of the baby universe, as I say, 380,000 years since birth. And then we have to sort of move that forward 14 billion years to get the right number, right? So I want to ask you some questions on that. And so we get a number like that. So we take a baby picture and then we predict what that baby is going to look like 14 billion years later, and we get a number. So that's a CMB number, cosmic microwave background radiation based Hubble constant. And then we are here and now, we could essentially look to stars and see if we can measure that in a different way. And you've been doing that for many decades. And we find, well, most engineers would think these are slight discrepancies, but for astrophysicists, these are major discrepancies. So there are some issues. So what do you find now? Last time we talked, you were using Hubble data, but now you have JWST data. So have things improved for you?
Oh, I think things continue to improve enormously in terms of the measurements that we can make. So Hubble gave us a huge leap over what could be accomplished with telescopes on the Earth, because we could get above the Earth's atmosphere. And the Earth's atmosphere, of course, is turbulent, and it smears out the light that is coming to us from these distant stars. And we're trying to measure the stars against the background of the whole galaxy in which the stars reside. And so this new ability to look with high resolution with Hubble let us measure Cepheids and then tip of the red giant branch stars much farther out and with much higher accuracy than we could do from the ground. And so when I talked to you 4 years ago now, our Hubble program was to measure tip of the red giant branch stars out in the halos of galaxies, and we can talk more about why that is an advantage if you like, again.
Yeah.
And we were able to make measurements of the distances to nearby galaxies that also had type 1a supernovae, these very bright objects that we can observe much farther away. And they're rare, the supernovae. They occur only once in a century on average in a galaxy. And so there are very few that are nearby enough that we can also measure stars like Cepheids or tip of the red giant branch stars that are much fainter than the Cepheids. That they're much fainter than the supernovae that we're tying into. And so with Hubble, we were able to make measurements that were far more accurate than we could make earlier. And with JWST now, we get another leap in resolution. This is a much bigger telescope. It's 6.5 meters in diameter as opposed to 2.5 meters, which Hubble is, a 100-inch telescope. And it's sensitive to the infrared part of the spectrum. So Hubble was optimized for optical radiation. That's what our eyes are sensitive to. And JWST is sensitive to longer wavelengths than our eyes can detect, to infrared radiation. And there's a huge advantage in the types of measurements that we're making because, for example, there is dust that is in the intervening regions between stars. And the dust has the characteristic that it will scatter light that's coming to us from these stars or absorb it so that the star will look fainter than it is intrinsically. And so if we can essentially get around the dust, the long wavelength infrared photons can pass by the dust, then that gives us much higher accuracy in the results. And the sensitivity, because it's a larger telescope, it collects more light, we get more signal. The combination of those two really allows us to move forward in accuracy. And as you described, we now have other ways of estimating how fast the universe is expanding, the Hubble constant, the expansion rate at the current time. And those are coming from really accurate measurements of tiny fluctuations, tiny differences in the temperature of the background radiation from the Big Bang. And those are now at a level of about 0.001%. It's a spectacular accuracy. And so from those fluctuations, you can measure the spectrum of those fluctuations and fit them with a model which cosmologists, astronomers now refer to as the standard model of cosmology. And that takes into account how much matter there is in the universe, how much dark energy that's causing the acceleration. And you can fit, the data are fit beautifully by this standard model that has about 1/3 matter and 1/3 of the universe in a form that we refer to as dark energy. And that tells you very precisely how fast the universe will be expanding today, given that standard model. And when you do that, you get a Hubble constant of about 67. With Cepheids right now, the value that you get is about 73 or 74. And with the red giants, when we started measuring those 4 years ago, when we first talked, we were getting a value of about 70. And so what we found now with our new JWST results is that we've confirmed the lower value, the value of 70. The tip of the red giant branch distances remain consistent with this higher accuracy.
Still different from CMB though, right?
What's that?
It's still different from CMB.
They're still different from the
Yeah.
CMB, and the question that we're trying to address is how interesting is this discrepancy? In the sense that if you want to test our cosmological model, the best way you have to test it is to measure the Hubble constant locally and see whether it agrees with what you get from the microwave background and the standard model. That's the test.
Right.
And so when I started in this field before the launch of the Hubble Space Telescope, we didn't know the Hubble constant to better than a factor of 2. People argued about whether it was 50 or 100. Right. So with Space Telescope, we resolved that uncertainty. We measured a value of 72 using Cepheids and also testing them with the red giant branch. And at that time, we improved the accuracy over this factor of 2. We could measure 10%. Now we're getting close to a few percent. And in fact, some would argue we've even measured it to 1%. I think that's a very difficult and somewhat elusive goal at the moment, but we are really improving the accuracy. So the question is,
sorry to interrupt, Wendy. So let me just set the context for the general audience. So what we're talking about is the expansion rate of the universe. And whoever is simulating this thing apparently put us at the center of the universe. You told me last time, no, everywhere is the center of the universe. Okay, so anyway, so wherever we look, things are sort of moving away from us. And so, suppose we sort of plot the distance to objects on the x-axis and how fast they're moving away from us on the y-axis, we get this nice little plot. And what we're trying to measure is the slope of that line, right? And if the assumption holds, which is universe is all the same in all directions, it has a constant sort of expansion, not a constant expansion rate, but a constant programmatic expansion, so to speak, then we should be able to measure that to some level. That's what we call H naught, here and now, what is happening. And we find that from different measurements, we're getting different numbers. And there are a lot of different implications for it, right? So am I understanding this correctly?
Yes. So, as you're saying, the Hubble constant is the slope of the correlation between the distance to a galaxy and its velocity. The farther away a galaxy is, the faster it appears to be moving away from us. And we measure that slope, and that is the expansion rate at the current time, the Hubble constant.
Yeah.
And so there are now many methods that we can use to measure the Hubble constant, and we're getting slightly different values. So this difference between 67 and 73 sounds small compared to the 50 and 100 that we had only a few decades ago.
Yeah.
But the question for us is, are the uncertainties now small enough that that's a significant difference? And if it's real, it would tell us that there is physics, fundamental physics, beyond the standard model that we don't yet understand. And so that's why it's really exciting. That's why we're spending a lot of time trying to understand, are there cracks in the standard model? And this is one of the most powerful means we have of testing if there's something missing. But what we have to ensure, and Carl Sagan said it well, extraordinary claims require extraordinary evidence. And I think there are always unknown systematics. Historically, if we look at where did the uncertainties arise, it's something that we didn't understand at the time. So we're looking very hard to try and understand, are there systematic uncertainties that are hidden that could be causing this discrepancy? And that's what we have to rule out if we're going to be in a position to say, yes, we need fundamental physics, something's missing from the standard model.
So it could be fundamental physics, and I'm thinking more tactically, Wendy. So I don't think this is correct. Sort of the spin of the Milky Way or the spin of the galaxy that we're observing. I suspect these motions are not really going to affect our observations, right?
Right. We're measuring simply the distance from where we are to another galaxy. And so, yeah, we don't need to worry about the spin of our own Milky Way, which happens on a time scale, which is very slow compared to where we're
I
making
saw
the measurement.
speculation. Sorry to interrupt. So I saw speculation the other day that the universe itself could be spinning, uh, and
Be,
could that be an issue?
People have been looking for evidence. Maybe the universe is spinning. There have been claims of that in the past. They haven't stood up over time. And I think, as people continue to analyze data, which are getting more and more powerful, we'll see whether something like that holds up. But again, that's not an issue for us measuring these distances.
Yeah. So what's your gut feel? So we have, I mean, they're sort of close, but they have error bars that are sort of overlapping now. It used to be sort of away from each other, but now they're overlapping. So what's your gut feel? I mean, are these things that we haven't thought about? Sort of local. So let me see if I'm thinking about it correctly. Localized systematics, meaning you know, so we get Cepheids at slightly higher value than TRGB and other methods. Is there something sort of local to Cepheids that we haven't captured, or something along those lines?
Yeah, I think I think for most people, the most exciting outcome would be fundamental physics that would have to
Yes.
do with cosmology. But we also have astrophysics. And what we're using to measure these distances are stars. It's not equipment that we have in a laboratory where we can tune the knobs and check for systematics. And we're using these stars that Cepheids are supergiant stars. They have very large radii, they're pulsating, they have different amounts of chemical elements in their atmospheres. Supernovae are essentially exploding bombs, and again, different chemical analysis, different elements in their atmospheres. And there's dust, as I mentioned before. Astrophysics may also be playing a role. And the question
Yeah.
is, do we understand the systematics of these stars that we're using well enough to say that we've measured this quantity to 1%? And so you ask what my hunch is, and I remain quite open to the possibility that there's new physics. That, for me, of course, would be the most exciting, to make a discovery of that kind. But I also remain open to the fact that these are measurements that are difficult to make, that ruling out systematics is it's challenging. And there are many
Yeah.
steps along the way to measure the Hubble constant, from very local measurements where we can measure a distance geometrically to the realm of distances where we can use Hubble or the James Webb to look at the tip of the red giant branch stars or Cepheids, out then step into the supernovae. And so at each step, the 3 steps to the Hubble constant, we need to ensure that we have uncertainties less than 1% if the overall uncertainty is going to be 1%. So I don't think we're there yet. And I think
Yeah.
if you realistically assess the current uncertainties, the value of 70 that we're getting is perfectly consistent with the value of 67 from the cosmic microwave background. But again, this is an empirical question. I remain open to, if we get more accurate data in future and it turns out that there is something fundamental that is missing now from the standard model, then that will certainly stand. But I don't see the extraordinary evidence that we would
Yeah.
require at the current time.
Yeah, so JWST, as you say, is making things more consistent, albeit, we don't have precisely everything coinciding precisely, but they're making things more consistent. So at least from the surface, there is no force toward abandoning lambda CDM. That's what it looks like, right? But on the other hand, I wondered, I mean, our engineering, our technology, are getting better. So as technology gets better, in some sense, we will bring things closer together. But if they're not aligning, it still means there is something out there that we haven't quite understood. And I'm not advocating for an abandonment level of CDM, but there's something there, perhaps, that we haven't quite understood. And that makes it exciting.
Yes, and I think what we call our standard model and just becomes a name, and it sounds as if it's okay, that's standard. But when you stop to think about it, it's a very unusual model
Yeah.
that says that there's 6 times more matter out there that's in a dark form that we don't yet understand what that dark matter is. And then 2/3 of the overall mass plus energy density in the universe is this dark energy that's causing the universe to accelerate. And we don't have, again, a fundamental physics understanding of what that is due to. So there are many puzzles in the standard model that remain to be explained. And so I think at some level, it makes just enormous sense to be saying, okay, we don't understand the standard model. Let's look for cracks, and maybe that will give us a hint as to what is going on. And whether or not that turns out to be a Hubble constant discrepancy, we don't know. And I think what's interesting is that there are well over 1,000 papers now that are on the archive, physics archive, astrophysics archive, that have tried to explain the Hubble tension. And no one has succeeded, which is just interesting how hard it is to break lambda CDM, the standard model, by trying to explain the Hubble tension. And so people have been able to get the Hubble constant up to 70 or 71, but 73 or 74, which is what the current Cepheid measurements are suggesting, has proved elusive. And so again, we don't know where this will end up. Yeah. And the other part of that is that when you try to solve the Hubble tension, there's another tension that has to do with large scale structure and the distribution of matter. People refer to it as the S8 tension. If you try and improve the Hubble constant measurements to come into alignment, you make that problem worse. So we reached a point at the end of the 1990s where there was a lot of indication that something was wrong with the then current standard model, because the ages of the oldest stars in our Milky Way galaxy seem to be older than the universe itself. The matter distribution on large scales didn't fit with at the time, the theoretical claim that the matter density was high. And just the stability of the universe, the flatness of the universe couldn't be explained. And then the discovery of the acceleration allowed all of those problems to be solved at once. It just fit, and it was a better fit coming from many different directions. And this Hubble tension problem has turned out to be really difficult, really challenging to try and solve. And it's interesting to me how difficult it has been to break lambda CDM. It's, maybe a solution is out there, people will find one, but they've looked really hard and haven't been able to find one. That's interesting.
Yeah, so it's comforting in some ways that we have something that is sort of foundational. I know nothing about this, Wendy, so I'm just sort of speculating a little bit here. So what if the expansion rate is not constant in the different directions that we look? So if you take all your sort of measurements across different galaxies and assume that those measurements are correct, do we find a pattern in any way that we might be able to use to think about the assumption, the fundamental assumption that the universe looks exactly the same in all directions?
Well, this was one of the questions, especially at the time when we were trying to settle the difference between 50 and 100 in the Hubble constant. And so you could ask, for example, if we lived in a where there weren't very many galaxies, we might be expanding faster in that void than the overall expansion. And so maybe that would be an explanation, that we would just be measuring a higher value locally than would exist on larger scales. But we're now able to make measurements with type 1a supernovae that go much farther out than at the time. And the ability to make measurements with CCD detectors, which we use for the Cepheids and TRGB and so on, they're much more accurate measurements. So the scatter in the Hubble diagram, this velocity versus distance diagram, has gone way down, and it goes much farther out. And so much tighter constraints now can be put on the issue of whether or not there are these variations over larger scales. And those appear to be at the 1% or less level. They're not going to explain this larger, potentially 9% difference between the cosmic microwave background and the Cepheids. And so, and also we would see the imprint of that in the microwave background. There would be fluctuations on those scales. So that doesn't appear to be the explanation for this. And it looked like a real possibility. I think it had to be taken very seriously as a way of explaining the difference earlier, but doesn't seem to work now.
Doesn't seem to work now. So where do you stand on this modified Newtonian gravity thing? Is there anything to it?
I mean, again, you want to test all these theories and you want to see where they break down. And I think in terms of modified gravity, if we look at galaxies like our Milky Way galaxy, and we look at stars that are orbiting about the centers of the galaxies, and try and explain how that the velocity of these galaxies changes as a function of distance from the center, you can modify Newton's laws, and you can say, okay, you can fit that, what we call the flat rotation curves of galaxies, and which was some of the first evidence for dark matter, that if there wasn't more matter there holding these stars bound to the galaxy, they would have flown off long ago. So the fact that the velocity isn't falling as you go from the center of the galaxy, but stays at a high value out to large radii was evidence for dark matter. So with modified gravity, yes, you can explain those rotation curves, but you can't explain yet, maybe someone will come up with an idea, but the fluctuations in the microwave background that we were talking about, and this really precise description of this standard model fitting this acoustic spectrum of fluctuations in the temperature and the polarization of the microwave background. So it fits in one context, but you have to explain a lot of things. And there are many other examples we could go into, but there's a limitation of that. So.
Yes, I talk a little bit to the younger kids who might be listening to this. So the puzzles haven't been solved. It sounds like that there's so many interesting puzzles. And so, kids going to schools, universities, there are things here that could be quite interesting, right?
Yeah, I think anytime you're at the sort of fundamental frontier of a subject, right, we're trying to understand things that are puzzles at the current time, and we don't know what in the end will be the resolution of those puzzles. But I think what is nice and what we saw in the development of the standard model was theory was being pressed by observations. New observations were indicating new hints that didn't come from theory in the first place. And so there was this really nice interplay between theory and experiment or observations. And we're at another period like that now. We're getting more and more accurate data on larger scales now. And so we're confronting our theories. And so that's the place where progress happens, is things don't fit for a while and you get better data or better theory and then better understanding. But right now we don't know where this is going to lead, where ultimately this will resolve. And that makes it exciting. We're learning something new.
Yeah, I mean, there's scope for contribution wherever you are, basically, right? So I want to ask you a slightly different question. So do you see any scope for machine learning here? It seems like we are collecting a lot of data. and we have different hypotheses. Um, and could we potentially use some sort of machine learning to extract information from this data?
So, potentially, absolutely, yes. We'll see what happens. I think a lot of where astronomy is going now are these very large surveys. And for example, the Rubin telescope is going to be operational very, very soon. It's going to get data from millions of galaxies, millions of supernovae. And so just the ability.
That's ground-based? The
Yes,
Rubin?
ground-based.
Yeah.
And there's a satellite called Euclid that is operational now, being run by the European Space Agency, ESA. And soon we hope to be launched the Roman Space Telescope, which is a NASA telescope that should be ready to launch in about a year or so. And those are going to amass huge data sets and are amassing Euclid already, data sets on galaxies and in that sense, machine learning, no individual is going to sit down and analyze the data for all those galaxies. And so I think what, of course, the hope is that with machine learning and AI, there are going to be new discoveries that will be done by AI. And if this is one of the examples where that will happen, we'll see. But I think things like protein folding and in other areas that are, poised to be solved by AI, where, it would take a graduate student apparently 5 years to do, one protein. Now AI, has solved the problem and, led to a Nobel Prize. So we'll see. I think the jury is out, and there will be some problems I think that AI is going to do much more efficiently, and some that will be done, I think, will be a partnership between people and AI, and some that will be best done still by people. So it depends on the type of problem. We'll see. It's exciting.
Yeah, it's really exciting. So I have a bit of bias here, Wendy. So I think astrophysics is very amenable to machine learning. Um, Biology, I'm not at all convinced that we have any clue what's going on in the human body. Protein folding is one thing, but when I was at a pharmaceutical company in the late '90s, when the Human Genome Project happened, everybody said in 2 years all diseases will be cured, and 25 years later we haven't cured any disease. And so, yeah, biology is a little different, but astrophysics actually could utilize this technology, I think, at some level, but I don't
Well, I
know.
think, yeah, again, these big data sets and trying to understand galaxy evolution and different models of cosmology and how you constrain those models, I think it's going to be very useful. And, there are claims that new physical theories will be discovered by AI, which would be terrific if that happens. We have to see. And it is a whole new window for exploration. And so tremendously exciting. The potential is huge. But there will be areas where it will be much better, and there will be areas, as you say, that may prove intractable for AI. But we'll see.
Yeah, so this is sort of a philosophical question. And I always argued that AI is never going to create the next Einstein or Newton or Maxwell. And there's a reason for it. But then AI could actually plow through large amounts of data that humans have. They can sit in front of the computer for 24 hours looking for a sulfide or, looking for some sign, right? Computers are great for that. But I'm very pessimistic that computers, AI in general, is going to come up with new theories that will take a human brain, I think. So yeah, I don't know. I mean, it's my bias. What do you think?
Well, I think I share some of that skepticism in general, but I'm open to seeing what happens.
Yes.
And I think I'm less skeptical than I would have been 5 years ago. And the rate at which things are moving
Mm.
is incredible. And so it's
Yeah.
hard to predict the future. And I don't know. I think the capacity for the imagination of the human brain is phenomenal. It's, we don't understand how the brain does what it does. And yeah, I guess I would just say I'm open. We'll see where it goes.
Yeah, so this is not new research, but I want to finish up with this. So let's talk policy a little bit. We are entering a regime where policymakers don't understand the value of science, it appears to me. And I'm not exactly sure where this is going to lead us, right? So it has dramatic long-term effects because, if it discourages graduate students, PhD students to go into fields that they believe it's not going to be funded for whatever reason in the future, we're going to, in 2, 3, 4 years, we're going to be in a completely different situation, right? So I don't have any solution to it. I'm just identifying the problem. So from inside academics, how do you see this?
Yeah, I of course am not a policy person, and I see science as it's one of the, in my view, incredible endeavors that human beings take part in, and the fact that it's self-correcting, that is, doesn't matter whether a discovery comes from a graduate student or a Nobel Prize winner, or it's evidence-based. And that has been something, I think, that science has had bipartisan support for a very long time. And I think most people, if they didn't take a very bad science course in university or high school, which happens, which is unfortunate, and I think collectively we need to make sure we're doing a good job of teaching science. But it is not only exciting, but it has real positive benefits for society and for people in general in terms of health and other areas. And so I think it's, and when I think it's not all policymakers who are down on science. I think we as, again, collectively, most people are excited by and understand the benefits of science. And so at the moment, it's not just science where things are now having a challenge. And as you say, we're losing students. People are going to be leaving positions, going to other places in Europe. And I think even at a very fundamental level, technology and science have allowed the U.S. to play a leadership role in many aspects of what we all depend on. And to cede leadership in this area to other countries, I think, is just enormously sad. And to take one example just from astronomy, we talked about the Rubin telescope, and this is a survey telescope that's going to find millions of objects. And we have 2 telescopes that are being led by groups in the US that are large telescopes that can follow up on the objects discovered by Rubin.
This is in South America, the last.
The Giant Magellan Telescope, which will be in Chile, and the 30-meter telescope, which is being planned for Hawaii. And those right now need funding from the federal government to be completed. And if they're not completed, Europe is well advanced in building its extremely large telescope. And so we've just handed them all of these objects that will be discovered by the Rubin. And astronomers in the US will not be able to follow up on them and make new scientific discoveries that will come from this facility. So that's just one tiny example. And so these things, the Roman telescope is almost complete, and we don't know what will be the outcome of whether or not it will be launched. And that, again, there's just so much effort that's gone into that, and so much exciting science that could come of it. It just would be, I think, in my in my view, tragic to lose those opportunities. But in so many senses, we have to play this leadership role. We shouldn't cede that and leave it to others to be the leaders in science. I think the U.S. has really benefited from what we have done, the people we have attracted to science in our country, and I see it now in colleagues who are having to leave. And why? Let's not do that. I think again, everybody can agree that science has been good. Maybe not everybody, but I think most.
So we have done this before. If you remember, we had this superconducting super collider in Texas. I think we dug all the tunnels, and the funding was pulled. But now it's in Switzerland. Um, Actually, a smaller one. And then there we found interesting things as well. So yeah, so I think for general public, it's a very difficult thing because there are no tactical benefits. It's not like it's going to reduce inflation or make cars cheaper or anything like that. And so it's very difficult to explain why this should happen, right? And I don't know if the academic community have really found a way to describe these things in a way that general public can understand. I mean, I can explain it. I don't know. I don't know how to do it. Well, what do you think?
I think, in a very practical way, of course, that scientific discoveries have led to advances in medicine that could save your child or your
Yes.
mother or yourself, your wife. Those are concrete examples of cases where people had genuine scientific curiosity. They may not have had, certainly in many cases, not known where the science was going to lead, but led to tangible things that have saved people's lives, including NMRs and equipment now that is in use in hospitals that have again saved people's lives. And even practical things like the GPS that's in our cell phones now.
Yeah.
Without Einstein's theory, both of special and general relativity, those satellites, the GPS satellites, would not be able to operate. And so
Right.
I think it's true. If people don't understand that, then we as scientists haven't done enough to help the general public understand how much of our modern life depends on scientific advances. And if you think, okay, cell phones were invented in industry, well, the scientific basis of that technology and the people who created it came out of universities, and you don't want to kill that partnership that has been so beneficial. And I think, yes, one hopes that an outcome of what we're seeing is that we can get rid of a lot of the barriers and things that slow down progress, and make things more efficient. That's great. I think everybody can be for that, but you don't want to, in fix it, getting at the disease, you don't want to kill the patient and you don't want to kill the scientific enterprise and things that have been going on for a very, very long time that are just coming to fruition, and cancer research and things that are going to benefit all of us. It just, it doesn't make sense to me as a scientist to say we're going to stop those things.
Yeah, so I don't know what the right solution is. I know that you have to go. The disconnect. We talked about the Hubble tension. The policy tension here is between people saying, "What am I going to get for it tomorrow, next month, next year?" And science advancements. Science advancements are very, very non-linear. We have no clue where that's going to lead us. It's very difficult for public, and I would argue the contemporary policymakers, to really internalize, right? So I think academics and scientists more generally have to come up with a language that convinces public that Yeah, there's this long-term investments we have to make that has uncertain outcomes. I mean, it could lead to nothing, but when it leads to something, it has tremendous impact on humanity, right? So there is an asymmetry in terms of benefits and costs. Most people don't understand that. So I think we have a huge problem here. Uh, I don't see academic institutions really getting this message out to people or anything. I mean, what do you think?
I think you're correct. I think it's a very difficult thing for people to appreciate, and we as scientists, I think, have to take part of the responsibility that we have not been effective at communicating what we do enough to people who aren't doing science or who may not be familiar with what is behind many of the things that they depend on in their daily lives and for their health and so on. And so you have to take suggestions from you. How do we do better in doing that? Because I think it does take a long time often. The research that goes into finding things that
Hmm.
ultimately are helpful to humanity can take decades to build up. And I think if we have the idea that, well, industry can do these things, we've had a tremendous partnership with industry.
Yeah.
And the students who are coming out of universities in scientific fields learn how to do things. They go into other fields often that is also a benefit. And and so it's, I think, something that we have to step back and really think about. How do we reach people who are not familiar with the science, but who hear, you know, that something was done by industry, or they don't, what was in their cell phones? Well, where did that come from? They're not imagining that Einstein, sitting in his patent office, who had no interest in having a cell phone, or couldn't imagine that there would be cell phones, was just thinking about gravity. So a lot of fundamental research is driven by curiosity. We are curious as human beings, and we want to understand, the scientists or the children too, right? We want to understand the world we live in. And a lot of that has led to incredible benefit for humanity. And that link, I think, is missing. People don't quite appreciate that a scientist in a laboratory working for 30 years has
Hmm.
developed a drug that will save, my child. And that's incredible. And I think people need to understand that, then we need to do a better job of communicating that.
Yeah. So to finish up with this. So I was thinking more tactically now. So Hubble and JWST um, in itself actually gave us a lot of information, very tactical information, engineering information, how to do things better, right? Um, and so we don't have to wait for 10 years for this benefits to happen. It will actually happen in a very tactical sense too. But what we haven't done for the public is to sort of lay that out in some sort of ways that they can internalize. And I don't know how to do it, but yeah, that's my perspective. Yeah.
Well, I think it is very difficult. And I think, explaining to people that technical challenge of launching a telescope that's made up of mirrors that have to unfurl in space, and space panels, and the technical, uh, I want to almost use the word miracle, to
Yeah.
achieve something like that is stupendous. And of course, there are spin offs that may not be obvious and may not be completely direct. But when we learn to do things like that, then it does ultimately benefit everyone in some capacity. And so, and the story in itself, let alone the science, just the engineering, is an incredible journey that we
Yeah.
can do something like that. And ultimately, we will benefit from being able to do these very difficult things in space. And so, um, yeah,
Yeah. So
I would take your suggestions for how to do better getting this word out.
yeah, we should collaborate on this. So sort of the multiple on um, societal benefit is very high. So, NSA and NASA budgets, it's a trickle, uh, to what our budgets are. It's nothing almost. And the multiple on that is like almost infinite in many ways. And so how do we portray this in a way that I don't know if the contemporary politicians really understand it, but in the long run, I'm thinking, 3, 4, 8 years down the road, I don't think most politicians really have any clue how these things work, right? So um, it's a bit of a political problem in the sense that, people say, these elites, University of Chicago, Harvard, Stanford, yeah, I mean, they're in a different world. Um, who cares about them? They say all this exotic stuff, but it doesn't make any difference to me. Um, we have to get over that bridge, I think.
I think, historically, science really has benefited from bipartisan support. I think that's just been a very long-standing thing. And I think, part of the difficulty that we face in many arenas is that the political cycle is 4 years or 2 years, and depending on the case. And so it's harder to think of things that require a longer term. And I think science is something, it doesn't happen overnight, a new scientific discovery. It can require a lot of time to get it to a point where it helps. But understanding that, and as you say, this is a minuscule fraction of the overall budget, but it has a huge multiplying factor. And, I've heard statistics and, I'm not an economist, but for every dollar that goes into science, you get $5 back in the economy. And so getting that message out, you were in this together and working together across universities and across industry, across, society in general. I think if we pull together, we do really good things, and we should look for opportunities to do that. And I think science provides one of those arenas where we really can do good things, and we should. So getting that message out, again, I would take advice from you how to do that, because I think it will be tragic if we cede leadership to other countries and lose what we have, which is clear leadership in science in the world and in medicine, health, and the things that have come out of scientific discoveries and that lead to technological advances, that lead to benefits to the economy. And we should be celebrating those and getting those with more support, not less. So I don't know how to say it better, but it's to all of our benefit. And I hope we can find a way to get the message out and to work with people to continue to do it.
Yeah, let's keep pushing. So I know that you have to go. So just like those engineers who made Voyager 1 and Voyager 2, they they made them work for 50 years. Little tin can thing that they set out. So let's keep pushing. I think at some point we'll get better. Yeah.
Yeah, I think
Excellent.
that's what we have to do.
Thanks, Wendy.
Okay, thank you. Thanks for having me a second time. That's a privilege.
Thank you.
Thanks a lot. Bye-bye.